So thank you very much. Welcome to my talk this afternoon. I'm pretty happy to be here again and be part of SummerSOC. Thanks for inviting me again.
Thanks for coming.
For giving this tutorial, because this gives me the opportunity to put together a few pieces of what we do and what we have already been talking about on previous SummerSOCs. What I wanted to do is to give you kind of the overall picture of what we think what is important in the context of real-time data management for big data. So I'm a database guy too, as Christoph, and I'm really happy that this conference has these two branches about service-oriented things and database things, and I think it fits perfectly together because what we're doing here is primarily building infrastructure for doing something like data or data management as a service in the cloud environment. Talking about data management, so it's about database systems, but it's not only about database systems. They are only a certain component within an overall infrastructure. We have to take other components into account. We're talking about for big data. That means we really want to deal with applications with very large data volumes, with continuously growing amounts of data, and that means we need to design these systems, these infrastructure to really scale, to be scalable. And additionally, we want to make all this by providing low latency data access. Real time actually means that you, as a user of a database or of a data management system, that you are continuously notified if something within the database happens which you are interested in. For example, certain writes, that means, or updates. That means we do not really talk about hard real-time restrictions, but our understanding is that real-time in this context means that within an acceptable time frame, you get notified when something happens, you have formally registered that you are interested in. Yeah. And this is the context, and I present work which has actually been performed by two PhD students of mine. Felix has been here on previous SummerSOCs and has given talks. Pretty interesting to know that both of them are these days submitting their PhD theses, so they cannot be here because they are busy on that. We're doing research on interesting things in Hamburg in my group. But besides doing research, some of what we have kind of doing research on has made its way being a product of a little startup which has been founded by Felix. This is the backend startup. And yes, they do web caching or real-time database data management and sell it as a product within this startup. And I will be talking about many different systems which are out there. Thousands of real-time databases, of stream processes, of NoSQL systems. And these two guys know every tiny little detail of each of these systems. I don't. So because I have them, I don't need to, I have them. So I will be focusing on giving you, as I told you at the beginning, the overall big picture, how things relate to each other, how are we can classify these systems in categories and we can assess these categories. And from that, we can derive why we did what we did in Hamburg, and this is what I will briefly tell you at the end of the presentation, if I have time. So I have about 1 million slides, so I need to hurry up, and if I'm skipping parts of the presentation or hurrying through slides, don't be worried. If I do that, it does not mean that it means that you don't have to understand the details. So then I will focus on the more abstract things and how they relate to each other. So what I want to do is, similarly to Christa, I want to give you a short history of data management, talk about NoSQL database systems, about data stream management a little bit. This is not so much of importance because much more important are the stream processes which are out today. And I will talk about those, and we'll talk about real-time databases, and then I will talk how we use all this and how we extend this in order to really provide a real-time big data management infrastructure in Hamburg. So this is the short history I want to do. Christoph was already telling us about the beginning of it all. In the 70s, we had the rise of the relation standard. We had 4 first prototypes. We had 4 first systems. We had the standard, and this is the basis for everything we are doing in database research at SummerSOC. Later on, we had some extensions in the direction of active database management. So we have these things like ECA rules, triggers, and so forth, trying to do something kind of automatically within the database. Afterwards, we had these complex event processing systems and data stream management systems. So they were kind of closely related to database management because although they were able to process streams, they had some underlying notions of structured objects, of schema, of relations between objects and complex events. So they were not really successful in the domain we are talking about, which is then the area of big data applications. So the first category of systems which were able to deal with that are the NoSQL systems or these big data processing infrastructures like Spark. And the next group I want to mention then is the stream processing. It's the category of stream processing systems. This is what I have been talking about at last year's SummerSOC, so I can skip that today. But these systems are not the last category to mention because we also have what we call real-time databases. And we will see that it is actually not sufficient what they provide. Actually, they promise it, they don't scale really very well. So all we need to do is to provide something our own, and this is our research at the end. So this is what it will end up with my talk. I want to first of all talk a little bit about database management, and I will directly jump into the NoSQL area. We have written a paper, it was published in SummerSOC earlier about NoSQL database system survey and decision guidance. When we started to do research on that, we often had the situation that people came to us and said, oh, there's a whole bunch of systems out there. They all do well, but we don't know which system is the best for our specific requirements, for the application we want to build. And then we thought we need to categorize, we need to assess all these systems and to help people to find the right systems for their special needs. So this is what ended up in this decision tree I want to go quickly through. The first split in this decision tree is about the access pattern. If fast lookups are really sufficient, then the next split is about the data volume. If your data fits into the main memory of a single machine, then we recommend to use systems like the key value store Redis or Memcache. Redis has a better functionality. If simplicity is of some matter for you, you should use Memcache. If you have unbounded data volume, so that you need a multi-node system in order to make things scale horizontally, you can further distinguish what is captured by the CAP theory. Certainly remember that. The CAP theory essentially tells us that in the case of a network partition, you have to manage the trade-off between consistency and availability because you cannot have both in that case. So if you really favor availability over strong consistency, if strong consistency is not a fixed requirement for your application, then we recommend to use one of these, for example, for shopping basket applications. If you have the requirement of strong consistency, then go for these systems because they are able to provide that. Okay, the right-hand half of the decision tree is about complex queries, when you need to work with complex queries. Again, we recommend to have the next split about the volume of data. If your data is HDD size, yeah, so you can manage it in a traditional way, then we recommend to do the next split with respect to consistency again. I don't know if you, certainly all of you know or have heard the CAP theorem. This is about what some kind of extension of the CAP theory says. It's called the PASEL. I don't know, is it a theorem? Doesn't matter. So it is saying, even in the case that you do not have a network partition, it does make sense to trade off in between consistency and availability. Yeah? So even though your data fits into a traditional machine scenario, if you want to do OLTP, then use relational systems or others here. But if you really favor availability over strong consistency, it does also, in these size scenarios, make sense to distribute things over a multi-node system, and this is can probably be done, for example, like CouchDB and MongoDB, and this is the actually the website applications. You know. If you have unbounded volume, and complex queries need to be optimized for latency, then again we recommend to use MongoDB, because MongoDB has a very expressive query language, and it's in the category of the NoSQL system, that system which is able to do optimization and things in the best way, in comparison to the others. So for example, and if you if you need to do analytics, yeah, and if then you, Christoph was also mentioning, you can use some big data processing framework infrastructure to do that, like Hadoop or Spark. I will come to Flink later on. Here we also have listed Cassandra and HBase. These are also suitable for this branch, but they excel at throughput optimized big data analytics when combined with Hadoop and Spark. This is why they are listed here, because they are well prepared to be integrated with such frameworks like Hadoop and Spark. So this is the overall thing, and it's not really the result of some experience or of our feelings what would best fit to a scenario. This is the result of an in-depth analysis of the techniques which are applied by these systems, which are applied internally, and we related these techniques like sharding, replication, storage management techniques, query processing techniques, with non-functional and functional requirements which are typical for nowadays applications. So for example, replication is good for read scalability. It's obvious, right? So in this way you can follow each of these relationships, and you can see which functional and non-functional requirements are kind of supported by which of these techniques. Then we went through all these systems. For example, sharding, you know what sharding is. We do some allocation of data on different nodes. Partitioning strategies can be hash-based or range-based. It's then difficult to manage joins and so forth. Nothing new. There's hash-based sharding. You have an even distribution, but you don't have any data locality. All the things we have already talked about in different earlier systems, and these are sampler systems who are doing hash-based sharding, we have range-based sharding. You know the advantages and the short backs. These are systems which implement range-based sharding. There's another thing like entity group sharding, grouping occurrences of specific entity groups together and so forth. We did it in the same way for all the others. For example, replication. Yeah, you have a DB node, and if the data object comes in, copies are stored on these three nodes. You then can further distinguish the consistency model. Do you do the replication synchronous or asynchronous? Do you have a multi-master or master-slave replication? Asynchronously means fast writes. You don't need to coordinate something, but things may become stale, inconsistent, right? Fast, but inconsistent. This is a thing which relates to the already mentioned availability consistency trade-off. Implementing these systems, synchronous, eager, things that consistent, but it takes you longer to do the coordination to keep things consistent. These are systems who are running synchronous. You have a master-slave. Only one master is allowed to accept writes, and it propagates these updates to the others, holding replicates of the same object. Or we do it multi-master, then again things are easier, writes are faster, but things are not really consistent. And you can combine all these. You have, for the when and the where, you can combine all the different alternatives, so you have 4 different ways to really do it. And for example, Redis is doing asynchronous master-slave replication. Storage management. Christoph was giving us some up-to-date information. This is what we already know. We have HDDs, we have SSDs, we have RAM, we have different techniques, and again, we can relate them to certain requirements you might have if you want to develop an application. So durability, so logging promotes durability of write operations, depend only input-output is increased write throughput. Update in place is good for read latency because you do not have to handle different copies of something. And in-memory caching is good for latency, because the data is closer to the application itself. And the same thing for query processing. If you have distribution, you can run local secondary indexing, fast writes, but you have to manage scatter-gather queries. Global secondary indexing, slower inconsistent writes, because it's more expensive to reorganize the index, but the queries are fast. Distributed query blending, and we discussed about that a little bit this morning, is very scarce nowadays in NoSQL systems. The best here is MongoDB, and they work on that. So it's getting better. So possibly you can do something for them. So analytics frameworks can be used as a fallback for missing query capabilities. We have this in our decision structure. So for example, Cassandra database can be easily integrated with Hadoop or Spark, and we have materialized views and all these things. So this was an example for hurrying through slides, but I hope you got the overall message. And if you are interested in how these different functional and non-functional requirements you might have if you want to develop a new application, how they relate to the techniques which are used within NoSQL systems, you can look into that paper and can use the decision guide in order to find the best system for your specific needs. So this is what we wanted to provide. Okay, so going further, active database. This is animation which is supposed to illustrate how things are doing today. So if you are interested in circular shapes, you need to ask the database. If then something is updated within the database, there are other circular shapes, you have to ask again, and then you get the complete answer again. But you are not informed when something happens within the database. Yeah? So in terms of real-time things, it might be appropriate to have the opportunity to register your query in the database and to get notified every time a circular shape is inserted or updated or created or something like this. Yeah? So all this, what is happening here is inefficient and slow. View maintenance, you know it. Yeah? So if you have a query, and in order to maintain the view, in the situation of modifications of database objects which are elements of the view, the other problem is you have to match every query against every update. Yeah, you have the query, you have the updates, then they have to decide whether or not to change, add, remove, or do nothing when a new data object is there. Yeah, and to notify. Similar processing for triggers, ECA rules, and this is the important thing here. The potential bottleneck is these mechanisms do not scale in both the number of queries and the write throughput, and the number of writes. Yeah? They do something, they provide something, active database features were there, they can help you, but they don't scale at all. So, data stream management. What we want to do is, again, some illustration. Every time an object is moving, an object is produced and provided into the stream processor, and as soon as an object enters this room, we want to be immediately be notified. Yeah? So this is what you think about when we talk about push-based access. Yeah? Traditional databases are pull-based. You have to ask and to ask and to ask to get a complete, accurate answer. What we want to do now is we want to register our query. We want the database to be push-based, to push the updates through along to you if you are interested. So, data stream management. You have a stream processor that has a working memory database. The objects are coming from the left, and then they are processed, and then they are archived or even forgotten. And you have applications which may register the queries. As every time a database object comes through, you get some answer, yeah? Which is kind of specified by the query you have registered. That's the high-level scenario. And data stream management systems like Borealis or Aurea, no, what was it? Aurora, what's your name? They provide things like that. Yeah, for different form, group, windows, aggregates, and so forth. They provide complex event processing. This is mainly about detecting patterns or groups of events which are semantic units or which need to be processed as units. I want to not go into that. Further important things are to distinguish arrival time and event time, to deal with that when developing such applications, and you have to deal with that clock skew, which is the difference between these two. Or sometimes it's prohibitive to really deal with all the incoming events. What you can do is to do sampling, just take every 10th object which is coming in, doing something with it in order to provide the best answer while avoiding to fall behind, because you're not able to manage the whole overall amount of data which is coming in. So, this is what we have, and this is what is not applicable in really big data scenarios. This is again a comparison. You can log into it. It's nothing very exciting. The message here is these systems are not sufficient to really do stream processing in big data scenarios. And this is the reason why stream processing systems were developed. And these are systems like Storm, SumSOC, Spark Streaming, Flink, and so forth. This is where I went into during my talk last year, SummerSOC. So I don't want to give you don't want to give you detailed insight in each of these systems. I just want to kind of assess the systems, compare them to each other. I want them to give you an assessment of the overall class of systems.
Why did you leave out Kafka? Or did you put it in and I didn't see it?
Kafka is actually discussed together with SumSOC because they came up together. So the overall, the more abstract things to take away from this part is, this is a general data processing pipeline. What you have here, data is coming in from people, from systems, from sensors, and then you have a persistence or streaming layer. And data may be processed as units, or if you do streaming, it may directly process as it comes in. Yeah? We directly pass the data object to the processing layer. So we are here, and this is what these systems want to do. They, in big data scenarios, have to heavily rely on scale out. This is what we also have been discussing this morning with Christoph's talk. And then you have to deal with all these things, deployment, monitoring, scheduling, how to do fault tolerance, and all these things. Yeah. I just want to mention that all of these systems have some means for doing scale-out, in order to deal with continuously growing amount of data with faster incoming data and so forth. So now, what are the options? There are many, many, many systems out there. Again, we wanted to kind of categorize things and to make things easier for people who have the hard job to select one of these systems, and then we kind of arrange them along throughput and latency. And this relates to further distinguish this class of systems into stream, really stream systems, and batch processing systems. Yeah. So, batch processing means the incoming data is first retained, yeah, in some database or some file systems which provide some persistence. This is necessary because you need to process data as units of objects which belong together in order to process them. This is what typical batch processing systems do. Yeah? And then the overall unit is pushed through the batch processing passed to a serving layer, and then who gives it information where it can probably be presented to the users. This is very efficient, but you have a high latency. You have to wait until the night is over because the batch is running all through the night and you get the results next morning. This is not really acceptable in those applications we have in mind when we talk about stream processing. This is about velocity. What happens here? Kafka or Redis, a streaming layer, data is coming and is directly pushed through. Yeah? It is somehow processed and you get something at the application side. So this is a low end-to-end latency because you directly push it through processing. The challenges are obvious. Somehow I will deal with long-running jobs. What about asynchronism? You have incomplete data. So actually, the most important thing is what you can implement here is something like a incremental algorithm. Yeah? Because you directly push through and do something with all objects we are coming in and present something. And the algorithms which can be implemented in that way are by nature incremental. So then people came up with this, at a first glance, elegantly looking idea of integrating these both things. And this is what is meant by the Lambda architecture. Here you have a real-time path. Yeah, you do immediately something with the data and present something, but you retain it in the second branch of this thing, and then you do batch processing, and then you kind of correct the things you have told the application. Yeah. Fast output through the real-time branch and data retention and reprocessing, and they have something like a eventually accurate for all that if you do implement these two things properly. And this is the problem because the overall thing is meant to be one application. That means these two branches need to semantically fit together. But you have two code bases and two deployments. So actually, this is a nice idea, but nobody does really manage to do that. Yeah? So, and then the easier way is the Kappa architecture. There you kind of stress or emphasize the stream thing. Nevertheless, you have something like retention here, but this is not meant for doing the batch processing thing. It is just a reaction to the situation that these real-time processing systems are continuously evolving. You have to change code very frequently. And if you have a new state here, then you can use retained data and replay it in order to test that, and to have possibly different branches here. And then if everything is okay, you can switch from the old to the new code. And for that, the retained data is helpful. Yeah? So it's not a batch processing thing, although there is some retention. Yeah, again, only incremental algorithms because this is actually focusing on stream processing. So this is the overall thing. Batch processing versus stream processing. I think I covered all these points. Then we have the popular systems to arrange them on this dimension, the spectrum between low latency and high throughput. We can do the following. So we have the batch systems, Hadoop Spark, or Amazon Elastic MapReduce. We have the stream processing systems like Storm, SAMSA, or Flink. Then later developments brought us something like micro batching. Yeah, and you have an extension of Storm, which is Storm Direct Project, which that's micro batching, or an extension of Spark, which is doing Spark streaming. Yes.
Why is stream incompatible with high throughput? Why is stream not over high throughput? Why that distinction? You have stream on the left side and you have high throughput on the right side. I could imagine that you have a very big pipe that you stream through and you compute over, and that is quite high throughput. Is this not what you meant with high throughput?
No, actually this is, yeah, I understand the question now. So actually it is stream and batch. Yeah, so it is meant by the inherent properties of batch processing. This is actually what is actually meant by throughput. You are right. You can also have high throughput if you are streaming. But to process data as units, and then this is what you always find in the literature, that batch processing is good for high throughut.
Okay, so different notion of
yes. Okay. We want to do stream processing because we want to work towards real-time data processing. And then I skipped the overall details of all the systems because I have been talking about that last year. And then I want to give you that comparison. And the major thing here is the latency. When we talk about real-time, we have to talk about latency, because low latency is the major requirement in real-time data processing. And here you can see Storm's the best. Yeah? The next best actually is Flink. So I want to just compare these systems with each other, because Spark is really good in doing batch processing and doing big data analytics as batches, following MapReduce, but they have unacceptable latencies there if we want to do streaming with it. Use this extension. This is not the actual intention of Spark. Yeah. So the message here is Storm and Flink show subsequent latencies at relatively high throughputs, with Storm having the lowest 99th percentile latency, so it's actually the best. But Flink is almost as good as Storm and has a much better, is much easier to use because it provides much higher abstraction for system developers. So Storm is really, really basic and hard to use, and it is the first one. So what we did in our research, as we'll see later on, we used Storm because we started doing that 2 years ago. If you would have to do it again, we would use Flink. Yeah, because it's better to use and provides comparable latency. So others are there, which I cannot mention. We do not change the picture and so on and so forth. So this is the summary. Storm and Flink in terms of stream processing are the two best solutions. Storm is very basic. Flink provides high abstractions, and it's easy to use and it's easy to develop applications later. So now we come to okay. Now we come to real-time databases. So and then I talk about systems like Meteor, Rethink, Parse, and Firebase. And again, I want to look at the big picture. So making database is push-based is again the primary question. I want to repeat this, to show this slide again and to remind you that in the traditional case, we always have to ask about the current state. Then we get the full answer and we are not notified about something which happens in the database. Query maintenance is actually periodic polling, and that can't be really effective. Yeah, so it's inefficient and it's slow. We need to do something else. So traditional database systems, especially the relational systems, are managing static collections of data. Static collection, they're completely pull-based. Then we have the data stream management systems. They kind of deal with persistent and ephemeral streams, yeah, but they do not scale, they do not really scale as well. And we have the completely push-based stream processing systems which deal with ephemeral streaming. They consider the data once it is processed and then they throw it away. So, and what we do now is we talk about this area because this is where real-time database management systems fit in. Yeah, and the most prominent examples are Rethink, Pause, Firebase. And I want to go a little bit into those. This is the part where I want to give you some details, just to show you that I even know some of them. So, Meteor. It's a JavaScript framework for interactive apps and websites. It has MongoDB under the hood. It delivers real-time results by providing full MongoDB query expressiveness. So it provides the full query capabilities of Mongo to the users. And it's open source, but it's also available as a managed service, which is called Galaxy, which is a platform as a service thing you can use. The history, it was originally Skydrake, then it was renamed, and then since 2015 is available as a managed service. So, how does Meteor provide real-time data management? So what you have the MongoDB, which is in charge of managing all the data. This can be highly distributed and have everything MongoDB is providing. And then we have the video application servers. And as applications, you can subscribe to these application servers and you can register your queries there. And then Meteor promises you that if a new data object is coming in, that this data object will be checked against the registered query. And if that new object kind of belongs to the result set of the query, you get notified. But as you can see here, applications do have one application server which mediates between the application and the database. So things are pretty easy in this scenario. If an application is updating an object over the same application server where your query is registered, then things are pretty easy. So this application server can just monitor and check things, match the queries and the objects, and give it back if necessary. The problem is, what happens if the update comes through another application server? Then it gets into the central database, and what they do is they repeat the query every 10 seconds. So they do periodic query polling. And this is again the same budget as we had in Material Fusion and so forth. So it doesn't scale at all. They realize that. So PollenDiff does not scale with queries, because as I mentioned. So they realize
they may only run the query and not optimize, transform, and so prepare the query. They just may execute the query, and that is not so inefficient, I assume.
Yeah, but if you really have thousands of queries registered, then the pull and diff mechanism does not scale in the number of queries. Yeah? So queries are registered at the application server.
But this is strange.
Why?
They should have the query at the database in an internal format, maybe pre-optimized.
Okay, we'll come to that.
Okay.
So the next approach, they realized that this is not very good, and the next approach is called block tailing. What they do is they use the MongoDB replication, which is a master-slave replication. So you have primaries, masters, and secondaries subscribing to one of the primaries. And that means the master, as soon as an object is updated, needs to propagate the changes to the copies of the data. And they do this by making the secondaries subscribe to the operational log of the primary. Yeah, so they have an op log, the operational log, and from time to time they push the overall operational log to the secondaries, and they can replay things, yeah, in order to make the replicas consistent. This is how it works. So if an object, if a write comes in, it is applied in the master, and then it is propagated to the secondaries by kind of broadcasting the op log to the secondaries. So now, what does it mean in terms of real time? If an object is coming in, it needs to be passed. This is what you said to the primary, which is responsible for that object. And then what they do in order to have all application systems recognize that there are changes which are possibly relevant for their applications, they broadcast, they register all the application servers as secondaries of every primary. Yeah. So that means now the application server, after having received the broadcast, yeah, can now check whether or not this modification is relevant for the registered queries and can notify the application. Sometimes updates are not complete, so that you possibly need to check back with the primary to get the full information about the new state of the object in order to decide whether or not you have to notify the application. Yeah. And then it can be delivered. Every media server receives all DB writes through uploads. So this is the example that you have a non-complete update. Yeah, so this is, I don't know, there are situations. The update is only saying something about the name and the score, but for the subscribed query, it's also relevant which game is playing. So this is a situation where you have to check back with the central database before you may decide whether or not this change is relevant for subscribed queries. But this is not so relevant here. The thing is, because every media server receives all DB writes through the oplogs, this becomes a bottleneck. For every write, it gets the objects from the primaries. And that does not scale in the number of writes this time. Either it does not scale in the number of queries, or it does not scale in the number of write operations. So this was Meteor. If you look into Rethink, you have the same picture, you have a bottleneck, it does not scale. Let's skip that. If you look into Parse, you have the same situation, more or less the same situation, it does not scale. Yes? Firebase. Firebase is possibly worth mentioning it a little bit more. Details to real-time state synchronization, does a real-time state synchronization across devices, so it actually meant to notify thousands of mobile devices out there coming in. It has a very simplistic data model. Actually, the overall database is one JSON object, a hierarchical object. Yeah. It has a very simplistic query model. That means there is actually no real expressiveness for specifying query. And they don't have a powerful query language. What you can do is you just can pick out one node in the hierarchy of the database object. Yeah, and if something happens there, you can inform them with it. Yeah, this is the history. It has been acquired by Google, and because, as you can imagine, it is bad in terms of doing real-time database management, it has been extended, and the new version is called Firestore. So they do really this, looks nice, but because of the dream model and the situation that the overall database is just a single JSON object, and they do sub-tree syncing in order to get the information which mobile devices need to be notified when a change has been coming in. And you have a limit, that means you have a very limited expressiveness in specifying your queries. Yeah? So this is an explanation actually of that. I don't want to go in that, and the query processing is pretty limited. And this is what they themselves say in the documentation. It is limited to 100,000 concurrent connections and to 1,000 writes per second in a single database. Yeah, and if you think about WhatsApp or something, this is ridiculous. It does not scale at all. Okay? And this is what they themselves tell the customers. So that's not good. What they did is they improved the data model. Now they have collections of data, so there are many documents within the collection, and they can relate it to each other in tree-like structures, and they improved the expressiveness of their queries by this. You now have logical AND for some filter combinations. That was it. Yeah? But you still have no logical OR and other things you actually want to have if you want to implement such a thing. And it's still limited in terms of write throughput. 500 writes per second per collection, 1 write per second per document. Yeah? So this is what you can get if you buy a system which is printed out. And I think this is by far not sufficient. So there are others honorably mentioned, but they do not change the picture, and this is the comparison. I just want you to look into the first 2 rows. Each of the systems which is out there does not scale either with the number of write operations which need to be propagated or with the number of queries which are registered. So we need something new, and this is what we provide. Okay, so in summary, we need to make things scale when we talk about real-time database. We want to have a sufficient expressiveness for specifying the queries. Does it make sense if we cannot specify queries? And additionally, we did something which makes the thing kind of pluggable and to also use legacy applications underneath. I will tell you in a minute how we did that. So this brings me to future directions and our research. I first want to give you an introduction into, or to tell you about the basic idea of our basic thing, which is called the Orestes protocol, and which we assume to have a possibly polyglot backend where you have possibly several of these NoSQL systems side by side, which are kind of managed and coordinated by a backend service. And we actually want to support web-based application. And our major concern is to provide really low latency in delivering data from the backend to the mobile device, which is possible on the other side of the world. Yeah? So, and we do that by web caching. The usual scenario is if somebody here is accessing a web page and the backend for the data which is needed is on a different continent, then there is some processing within a system which is kind of computing something and putting things together, which are then delivered via the internet in order to be able to display them on the mobile device of the user. Yeah. So, you can increase bandwidth of your internet, but this is really limited. And there's a threshold from which on you cannot further reduce the latency. Yeah. This person has to wait for its data. And what we do is we exploit existing web caches, which are overall in the world. So if you access some data which is delivered through the internet, it is the data object pass several caches which are there in the internet, which the data is cached in, but these caches are currently not really exploited if somebody is accessing data from a backend, which is on the different continent. And what we do is we store all the data in these caches and enable mobile devices to load the data from the nearest cache, which is available there. This is a pretty easy idea. Yeah? But the thing is, how can we manage all that? Because we cannot rewrite the internet. We cannot change HTTP. We need to live with what the standard says. Yeah? And we found a way to extend all that and make it compatible with all the standards. So the effect is that we have less processing within the backend because the data is in the caches. And the problem now is, provided that we succeed in managing all these caches, the next problem again is if you do caching, you need to take care for ensuring for making your data consistent because you have to deal with copies. You do store copies within the caches. And copied data can get stale, inconsistent, right? If somebody in the backend changes the data, then the caches need to be invalidated. So if you look through, you look to that caches, you have two kinds of caches. There are things like content delivery networks, which are invalidation-based caches. That means the backend may invalidate the content of the cache. So if somebody changes an object in the database in aloud can inform the cache that there's a new version and propagate it there. But there are other caches which are closer to the web browser and to the application, which are expiration-based. So they get a time to live. That means data objects expire in the caches. So you need to find a way to deal with these caches in the case the data is getting updated and it's stale within these caches. And in order to, if the applications want to only have consistent data, yeah, they can do that, or they use data which is cached by exploiting a data structure we have kind of developed, which is telling the application which objects are stale and which are current, which are in the current version. And this is called the cache sketch. So what we do is we have the backend. We have some applications possibly modifying data within the backend. This is multi-user as always. This is just one example for invalidation-based caches, content delivery networks. And backend is working together with, for example, Akamai, which is providing content delivery networks. And the browser cache is a very easy example for an application near expiration-based cache. Yeah? So what happens now, if the application is requesting some data from the backend, we deliver it through the internet, and the object is cached on all caches on the way through the internet. Then we assume that an application modifying that object. Yeah, we are exploiting a Bloom filter. It's actually a counting Bloom filter. This is why we can have higher numbers here. They're not that important now. And as soon as modifications are happening, the backend informs the invalidation-based caches that there are new versions of the object and propagates it there. If now the application wants to notice that there's a newer version, it exploits the Bloom filter, which can be exchanged periodically, and do the same hashing, yeah, and then detects from that whether or not the object it has in its cache is current or not. Yeah? If not, it can kind of access the data newly from the backend. If it is still current, it can use it further on. Yeah? And this cache cache sketch information is, of course, delivered in the same way. Yeah? But this is a very small data structure. Where is it? For example, with 20,000 distinct updates and a 5% error rate. Error rate does not mean that there are really errors. You're talking about false positives, that you go through to the backend although the data is still current. Yeah? Then you have a size of 11 kilobytes. Yeah? It can really be kept small and it's really handleable. And in this way, an application can say, give me please the cache sketch every 10 seconds. And then you have a status window of 10 seconds. If you want to be really strongly consistent, you have to go always through, that's clear. But we are talking about these new applications where you kind of do these trade-offs we are always talking about, and when you possibly want to adjust your level of consistency, you can do it better. This is the message here. So, and this is the overall framework, and this is where we build our real-time facilities on top. Do I have time? Okay. What you want to do is, for example, if you have such an e-commerce scenario and the user is interested in the most popular products that are in stock, he registers the query, and as soon as something is changed here, it might cause the result set to be added by some object to be changed, or some to be removed because there are updates in the backend. And this is what we want to be the user automatically notified about. So what we do is this is the overall thing. We allow users to register their queries to our infrastructure. Then we have a kind of stream of all the update operations coming in. We provide them in a highly distributed infrastructure, which we realized by Storm. This is what I said earlier, that we used Storm. Nowadays we would use Flink for that. Storm is okay because you don't need higher guarantees, for example, as they are provided by Spark or Flink, and it shows the best latency in processing, as we have saw from you saw at the comparison we did earlier. So, and no, one more thing to mention. If something is coming in with this, which is relevant for some of the queries, the data is not only provided to the caches. This is how it relates to the Erasmus framework I was discussing earlier. And additionally, the corresponding applications are notified. Yeah. So,
sorry, do you send actually the new content, or do you only invalidate?
We invalidate the caches and we send the new objects to the client who is interested in it. Every modification of the result set, but we only provide the diffs. Yeah? Okay, so sensor data is coming in, we have this pops up infrastructure, somebody is interested in some object fulfilling some certain predicate, then the data, the updates are coming in, they are directed to certain processing nodes, and if something happens that is relevant for that application, then the match is delivering that, is deciding that, and then this is passed through. Yeah, it's just the object.
What is that in the middle? Are those Storm?
This is InvaliDB, and this is a staged real-time query processing engine, and the infrastructure in the middle is responsible for doing these match decisions. So, and what we have is we kind of had to implement basic features of the MongoDB query language, but the most, so that we have ordering, joins, and aggregation and engagements and all these things, because we wanted to make this pluggable. Yeah? So we had to implement query capability processing ourselves. But the most interesting thing is what you are, I think, asking about. We have this distributed infrastructure, and this is where we use Storm. Yeah? We build this on top of Storm. And if a query comes in, we kind of distribute the query to several partitions, so that we have as rows object partitions and as columns query partitions. And then we can, this way, do scale out of these matching processes in the situation that you really have many writes coming in and that you really have to manage many queries. And this makes things scalable. And then we scale with queries and writes. And this was what all the other systems were not capable to do. Implementation on Apache Storm, topology in Java, MongoDB query language, and this is pluggable. So that is also legacy compatible. So we can use actually arbitrary database management systems in the back end of our back end system. So it's we currently use several NoSQL database systems and relational systems. Okay, and this really scales linearly. So even under high latency requirements, which are kind of service level guarantees, something, you can, by increasing throughput and the number of matching nodes, you can show that all this scales linearly. And also interesting is that the distribution, latency distribution, does not differ much in situations with different numbers of nodes. Yeah, this is also important. We have the same behavior no matter which nodes are currently working there. We have all this described in much more detail in this paper, which we had at VLDB last year. So if you are interested, please look into this paper. It has everything about the details on that. Okay, so I guess I ran out of time.
Yes.
We did this here, an example, at Google, we subscribe to a tweet stream, and then if you just register some of the keywords, you get immediately informed if a tweet is coming in which kind of has this keyword in there. This is just some demonstration. Yeah, on backend, this is what the startup provides. It's the platform for web applications. It has additionally a speed kit, which is based on the new service worker standard. You possibly might know. It is kind of something which is running in the background of your web browser, which allows you to. This is with speed kits. You can just use backend on top of an existing application. The service worker is kind of capturing all the requests going to the original website and redirect it to the caching infrastructure we have. And then you can speed up existing web applications like this. And what they do is they use this service worker concept there, and originally the accesses go from the browser to the backend, and what they do now is they capture some of the requests and they direct it to backend, which then communicates with the original website. And this allows to make things much faster. There are several open questions, for example, how to adjust the times to live in the expiration-based caches. For that purpose, we want to use, and everybody wants to do, machine learning things. For example, reinforcement learning in order to automatically adjust these so that we have, as times to live, the real modification intervals of specific objects. And this makes things even better. And we have a fully cloud persistent data. I skip that. It's interesting too. And there's a lot of interesting stuff to do with distributed transactions. Currently we use VSIS Plus, because we have versions of objects in the caches, optimistic message transactions for that. Yeah, and then it is important to reduce the number of aborts and so forth. Yeah, and this is how it fits together and how you got it from my fast presentation. Sorry to be that fast, but I wanted to tell you everything.
Okay, thank you, Norbert, for your Thank you for your presentation. It was very interesting. Do you have any questions?
So now we can discuss about how to integrate your things with MongoDB in our study.
now we continue with the symposium. We have 3 papers to be.
Thank you. Thank you. That was fun.
So we're going to have the next paper by Manuel Fritsch. Okay. Okay, please.
Okay, thank you very much. So, welcome to my talk. My talk is about quality-driven early stuffing for explorative cluster analysis for big data. My name is Norbert Ritter, as already mentioned, and this is a joint work together with my wonderful colleagues Michael Behringer and Holger Schwarz. And we are from the University of Stuttgart at the Institute for Parallel and Distributed Systems. I'm working on explorative data analytics. The question is,